Hi, in this video we'll discuss about the velocity, acceleration and energy for simple harmonic motion. Let's say the displacement of the particle showing SHM is xt equal to a into cosine of omega t. Okay. Then the velocity will be vt equal to dx dt. Okay. So this is equal to minus of a omega into sine of omega t. Okay, because if we take the derivative of cosine of omega t, then it will give us minus of omega into sine of omega t. So dx dt will be minus of a omega sine omega t. Okay, let's say this is equal to minus of v max into sine of omega t, where v max equal to a times omega, because we have written v max because the maximum value of sine omega t is 1. So the maximum value of v will be a omega, right? So that's why we have written v max equal to a omega. Similarly, the acceleration will be a equal to the rate of change of velocity. Okay, that means dv dt. Okay, so this is equal to minus a omega square into cosine of omega t. Okay, because if we take the derivative of sine omega t, it will give us omega into cosine omega t, right? So dv dt will be minus a omega square into cosine of omega t. Okay, so this can be written as minus of a max times cosine of omega t. Okay, where a max equal to capital A times omega square. Similarly, for the simple pendulum, if the angular displacement at a given time t is theta naught times cosine of omega t, the angular velocity, that means rate of change of angular displacement, this is equal to d theta dt, this is equal to minus of theta naught omega into sine of omega t. Okay, we can express it in terms of linear velocity. Okay, if the theta naught is very small, then the bob shows very close to the linear motion. So that will be v equal to the length of the string, that is L times the angular velocity. Okay, so this is equal to minus L theta naught omega into sine of omega t. Similarly, the angular acceleration theta double dot, this is equal to rate of change of angular velocity, that means d theta dot dt, this is equal to minus theta naught omega square into cosine of omega t. So the linear acceleration a will be length times the angular acceleration. Okay, this is equal to minus L theta naught omega square into cosine of omega t. Now, in order to compare how the phases of the displacement, velocity and acceleration are related by, we may express sine function as a cosine function so that we can compare it. Okay, so we may write it as v max cosine of omega t minus 3 pi by 2. Okay, and this term minus a max cos omega t can be expressed as a max into cosine of omega t minus pi. Okay, this minus sign absorbed here. Okay, now we can easily compare the phase difference between displacement and the velocity is 3 pi by 2. Okay. And the phase difference between velocity and acceleration is pi by 2. Okay. And the phase difference between displacement and acceleration is pi. Okay. That means they are out of phase. Now let's see how the displacement, velocity and acceleration change with time. Okay. Now we can see that the acceleration A always acting towards the equilibrium position, and its magnitude is maximum when the magnitude of the displacement is maximum, and it is zero at equilibrium position. On the other hand, at equilibrium position, velocity will be maximum. We can see also from the graph that the displacement and acceleration are in opposite phase. Okay, that means when the displacement is maximum, the acceleration will be minimum, and when the displacement is minimum, and acceleration will be maximum. And we can also see that the phase relationship between the velocity and acceleration is pi by 2. Okay. Now let's take an example. A spring mass system is oscillating with the time period t. Okay. And the displacement xt equal to a into cosine of omega t. Then find the minimum time to reach half of the maximum velocity. Okay. So the displacement xt equal to a into cosine of omega t. Okay. So the velocity will be vt equal to dx dt, that is equal to minus of a omega into sine of omega t. Okay. So we can write it as minus of v max times sine of omega t. Okay. Where v max equal to a times omega, because the maximum value of sine omega t is 1, so the maximum value of velocity will be a omega. Okay. So at t equal to 0, the velocity is 0, because at t equal to 0, sine omega t is 0. Okay. Now let's say at the time t, the magnitude of the velocity will be v max by 2. Okay. And we also know that the t will be somewhere where sine omega t is positive. Okay. So the magnitude of the velocity will be v max into sine of omega t equal to v max by 2. Okay. So that means sine of omega t equal to half. Okay. And we know that the value of sine pi by 6 is half. So omega t equal to pi by 6. Okay. So that means t equal to pi by 6 omega. And we also know that omega equal to twice pi by the time period t. Okay. So the minimum time taken will be the time period t by 12. Okay. Now let's take another example related to velocity and displacement. Okay. Here a particle is showing SHM where the displacement xt equal to a into cosine of omega t. Okay. So what will be the trajectory of the particle in the phase space? Phase space is a space which consists of all possible values of coordinates and its conjugate variable, that is momentum. Sometimes to understand a physical system, it is necessary to understand how the position and the momentum changes simultaneously. Okay. So in order to visualize, we need to draw a phase space diagram. So here the position changes as xt equal to a into cosine of omega t, and momentum pt equal to mass times velocity. Okay. Her velocity is dx dt. Okay. So that is minus of a omega sine of omega t. So the momentum will be pt equal to minus of m a omega into sine of omega t. Okay, let's say this is equal to minus of p naught into sine of omega t, where p naught equal to m a times omega. Okay, so xt by a its whole square plus pt by p naught and its whole square, this is equal to xt by a will be cosine of omega t. So cosine of omega t is square plus pt by p naught, that will be minus of sine omega t. When we will take its square, so it will be sine of omega t square. Okay, so this is equal to 1. This is the equation of an ellipse. Okay, so in the phase space, the trajectory of a particle showing simple harmonic motion will be elliptical in nature. Okay, so if we draw the diagram of an ellipse, it cuts x-axis at x equal to a and it cuts y-axis at p equal to p naught. Okay,